Everyone wave! And that's right. Now, no more selfies with me, alright? No. Only if you bother with mine.
Okay, ladies and gents, this man needs no introduction, clearly. Matt Taylor is an absolute privilege to have here. For anybody that doesn't know already, he's a project scientist on Rosetta. They're mapping 67P. It has been on the news once or twice, I think. He's going to tell us all about the latest results of the mission to explore the comet. And I won't keep you any longer. I want to hear it.
Cool. Actually, what I'm going to do is tell you everything about Rosetta. So I'll encapsulate the entire project. Hopefully I'll finish in time. But because a couple of people had asked me how somebody like me got to where I am, because nobody can believe that, I thought I'd give you a potted history of me, just because I've had a couple of people asking. Right. I was born in 1973, that way you can now update Wikipedia, near Chelsea, but I don't talk about that very much, but I lived most of my life in East London, a place called Manor Park, which is on the Liverpool Street line going near West Ham, basically. I went to Meany Road Primary School. Look, see, that's an Amiga up there. Not an Amiga, it's an Atari console. That's when I was very young, and there were 4 buttons on that TV, I think, 4 channels. Mayfield High School, GCSEs, not many, not great. A-levels, 3, that's all you needed to get into university, and I had the hair for it as well. Then I went to Liverpool University to do a 4-year master's, the Master of Physics degree. It was the first time they were running it in physics, yeah. Liverpool, you can prove, always prove that it's Liverpool, it's one of the cathedrals at the background there. And then I went to Imperial College to do a PhD in magnetohydrodynamic modelling of plasma flows around funny geometries. It rolls off the tongue. And that's me celebrating getting my PhD. And then I went to Mullar Space Science Laboratory as a postdoctoral researcher on the fantastic cluster mission. It's still running, brilliant mission. Oh, how I miss it. So I was there for 2 years. Then I went to this place. This is Los Alamos lab in New Mexico where they built the bomb. And I was working on cluster there on energetic particle instruments. And that's on the ski hill there, being a typical Brit, going for a walk in a pair of jeans and a pair of boots in the snow. And then I went back to Mullar Space Science Laboratory in 2004, 2005, which is this one on the left again. But there I was working as an operations support personnel, working on the Double Star mission, which was a Chinese mission that were using spare parts from cluster. So there I had a bit of experience of how to operate instruments. Right. And then I'll talk about what I did, and then I joined ESA. So I applied for a job to be a deputy project scientist of cluster. For some reason they said yes, and so I went to ESTEC, which is in Noordwijk, which is kind of, here's Amsterdam, here's Rotterdam. Noordwijk's about there on the coast. It's the biggest ESA site that we have. So I was working on cluster. It's a fantastic 4 spacecraft mission looking at the interaction of the solar wind with the Earth's magnetic field, the science behind the aurora, etc. Plasma physics will be a theme of this talk. It will bore the tears off you. Anyway, and I was also a study scientist for a candidate mission, which is like a mega cluster with multiple spacecraft. Then I became project scientist in 2009, and for some reason they decided to make me project scientist of Rosetta in 2013. Right, that was me. Now we will talk about why we look at comets, why they're interesting, some comet observations, then I'll get to Rosetta and 67P and where we are now. You're all too young to know who this guy is. He's Lovejoy. It just reminds me to say that this comet is Lovejoy from the ISS, or one of Lovejoy's comets. He's found quite a few of them. Right, okay, what's that mean? You won't see it very well because the light's down here, but this is supposed to represent what happened at the beginning of the solar system. There was a big load of dust and gas. It collapsed, formed the sun, which will happen in a minute, hopefully. You get an explosion, and then the resulting disk of material started to collect itself together, aggregate, and you have the planets forming. So there's the sun kicking off. And then you'll start seeing, come on, hurry up. Anyway, you'll see, yeah, the planets forming, right? And from that, you had the planets and the moons, but then there was a load of stuff left over, and that's what we call the small bodies of the solar system today. They are the asteroids. These are asteroids yesterday, in between Mars and Jupiter. A lot of rocky stuff, and then further out you've got other small bodies. These are the comets, which we find a bit nicer, a bit more interesting, because they've remained on the outskirts of the solar system. You have the Kuiper belt, which is that on the disk of the solar system, and then the Oort cloud is further out. Actually, the Oort cloud goes out to about 1 light year away from the sun. That's the reservoir of where the comets come from. It's interesting because they've been there for quite a long time, perhaps since before the sun actually ignited. So this is really primordial material. It's the building blocks of what the solar system was made of. That's why we look at comets, because they've got all of this stuff from that long ago. As they come towards the sun, I'll show that in a minute, they become this entity that is possibly and hopefully familiar to you. You have this dust tail, because there's dust coming off of the comet, there's gas as well, and so you get a gas tail forming. And with the interaction of the sun's radiation and also the outer atmosphere, the solar wind, you get plasma as well. The key thing being is this entity in the sky is very, very large. You'll see some, I'll show some images later, but it's all coming from a very tiny nucleus. Actually, this is a different nucleus to the image I'm showing. That's Hale-Bopp, but this is the Halley nucleus. So it's a very small nucleus, and this tail and everything are tens, sometimes hundreds, even more thousands of kilometers in size. You can't see them when they're far away from the sun, but as they get closer to the sun, they're an icy dusty mix, or a dusty ice ball, or a frosty dust ball. I think we're now deciding from what we're seeing. And so that ice starts to sublimate. The pressures in space are such that you don't go through the liquid phase, you go directly from a solid to a gas. That sublimation process tends to bring off dust as well, and you get this fantastic tail forming. When you go through perihelion, closest approach to the sun, that's when, around that time, when everything's really, really active, because you've got the most energy input. So what have we seen from comet observations? Well, we go back in time to China a couple of thousand years ago, and these are silk texts that they've drawn, what they can see in the sky. Probably being a bit emotional as to what they are. They're a bit superstitious. If you can read Babylonian on this text, you'll see that they mention Halley's Comet. This features in a couple of the slides that I'm going to show. They calculated once we had discovered Halley, you can go back in time and work out where it was, and they reckon that Halley's being discussed in this tablet as well. They were signs of possibly doom, or a harbinger of doom, a sign of foreboding. This is the Bayer Tapestry, and this is the only Latin I know, Isti Mirenti Stella. They marvel at the star. That star is actually Halley's Comet as well. So depending on what side of the English Channel you were, was whether it was a good or a bad luck charm. Certainly bad luck for this fellow. And then on Wikipedia you can find things like this. The fact that the author Mark Twain was associated with Halley's Comet. He even predicted what was going to happen to him. So he was born on one of the Halley apparitions and said, I'm going to die when Halley comes back again. And he did. But then again, if he wanted to win the bet, he's the best person to be able to make that happen. I don't think it was suicide. Then we jump ahead of time in a little bit, and we start seeing our ground-based scientific analysis, scientific observations of comets. So we go from superstition to actually what they really are. These lumps of icy, dusty muck that heat up and start to throw stuff off as they go past the sun. And we get to see what they're made of through different wavelengths of light, and you see spectral analysis of that, so you see certain peaks in the wavelengths of light, and that tells you what they're made of. And you can see different activity around the nucleus as well. With the SOHO spacecraft, we see this sun grazer coming in. It doesn't make it round because it was too close. It broke up probably around the sun. It probably didn't, well, it wouldn't have caused this coronal mass ejection. It just happens to happen at the same time. SOHO, I think, has made the most identifications of comets in space. This one you probably can't see that well, unfortunately, with the light, but you can see, this is Solar Dynamic Observatory. You can see this comet flying across the disk of the sun. And the key thing you can see here are the tendrils of magnetic field and plasma coming off the surface of the sun and kind of interacting with the tail. Plasma. It's really cool. Then we have the Herschel Telescope, another nice space mission from ESA, which is measuring water of a certain class of comets. Actually, you can look at different flavors of water, deuterium to hydrogen, of many bodies in the solar system. That's what I showed too early, actually, for my liking. On the right-hand side here, you have Earth's flavor of water, deuterium to hydrogen. You can compare it to other bodies, and this basically gives you an indication of how these things have evolved in time. These bodies have evolved in time, and you can match where that water may have come from. A key question that we have in terms of solar system evolution is early in the solar system, the Earth, we think, boiled all of its water off. So for us to be here and for us to be able to drink wine and beer later on, the water must have come back. And we look at this deuterium, this flavor, deuterium to hydrogen ratio to find what could have done that. So you match it up. For these Herschel results, they actually showed that some Jupiter-class comets had the same flavor of water as Earth. So demonstrating possibly they were a viable delivery mechanism. We also see here that asteroids are shown to have that similar flavor. So these small bodies in the late heavy bombardment early in the solar system were likely to have delivered this water back to Earth. An important thing there is other observations we've made of comets recently, we found glycine, so building blocks of DNA in comets as well. So with the water, they may have delivered the building blocks of life as well. We have other observations. This is not a comet, this is Jupiter. And we pointed Herschel at Jupiter. I mean, you can look at the upper atmosphere and see that there's a dominance of water in the southern hemisphere. And Jupiter's like a magnet, we think, for comets, and has actually been possibly has protected us over the years. If we look at these images, I was lost off the top here, but nonetheless, this is Schumacher-Levy, which smacked into Jupiter a long time ago, but all the impacts were in the southern hemisphere. So kind of giving you an indication that these comets still do come in, but because Jupiter's so big, it tends to drag things away from us. I think it's something like 8,000 times more likely to get stuff going to Jupiter. So it's a great protector and filter for us. So it's not only Bruce Willis that helps us, it's Jupiter as well. And you can see the scarring from this Hubble picture down there. Then we jump ahead, no, we jump backwards. Which way do we go? Backwards, yes. 1980s, Giotto, this is Europeans' first deep space mission to go to Comet Halley, so it comes up again. Giotto was named after this Renaissance painter, and when you go on Wiki to find these images, you find out there was somebody on Star Trek that was called Giotto as well, but it wasn't him. There's a German slide showing there was a flotilla of spacecraft going to Halley. In fact, ICE has come back, well, kind of came back to life recently. But we had all of this, American, Japanese and Russian satellites, but Giotto was the one that got closest to Halley and really gave us these great images. Well, one of them is. The one on the right, it unlocked the fact that we had a comet nucleus that was rather solid, that it was interacting with the sunlit face was the one that was becoming most active. And we really began to get a good idea of, well, a nice idea of what comets were in the nucleus. Now, the plot on the left, so the story goes, was seen by a particular prime minister at the time, and is why she didn't like space at all and kind of wrecked our industry and our science for a good couple of decades. So she didn't like the colour, said space is rubbish, and then spent money on other things. But that's the story I've heard. This is the space plasma team, Muller Space Science Laboratory. If anyone knows Andrew Coates, he actually still looks like that. I don't know how he manages that. Anyway, but this was Alan Johnston's plasma analyzer. And for record, that's what I looked like at the same time, up in the top left. The BBC Horizon programme was covering the Halley flyby and also a subsequent flyby of Grigg Skellerup. And during these programmes, they started talking about this mission, and you can find it on the interweb. That somebody has uploaded this, probably shouldn't have. But you can see this snapshot at the end. They start talking about Rosetta. At the time, it was, as you can see here, a comet's nucleus sample return. So the plan was to send something up, grab a bit, and bring it back to the laboratories on Earth. That was a collaboration between ESA and NASA, and as usual, things didn't go that well. And also, it was shown to be a bit too extravagant for what we could do at the time. And we had to modify our plans for what that mission would be. And it turned into the Rosetta that we know today. We've had a number of missions after Giotto. These are, I'm listing only the ones that have imaged comets. There have been other ones that have detected them. Even the Ulysses spacecraft detected a comet tail. So we have the Halley Armada and then deep space stardust, deep impact. The key thing I want you to see, if you can see it down the bottom there, is these are all flybys at 100 kilometers or more and at very high velocities, tens of kilometers a second, up to 80, hundreds of kilometers a second. They really were just providing with a snapshot of what that comet looked like at a point in time. Now, that's why we needed Rosetta. Even at Giotto, we knew that was the next step. That's what we had to do. And we had to get very close to a comet and get into walking pace to basically ride alongside the comet and see it evolve as it went through its closest approach to the sun. Okay, so now we start talking about Rosetta. Just check the sound on. Rosetta Stone, I actually gave a talk on Thursday in the Museum of London. It was a commemorative lecture for Colin Pillinger, and we gave a nice combination of actually Egyptology with Rosetta, so from ancient to now. And that link is to do with the Rosetta Stone because it was thought to, well, it was the mechanism alongside the Philae obelisk in unlocking the secrets of the Egyptian language, the Egyptian hieroglyphs. And we use an analogy that Rosetta's there to unlock the secrets of the solar system. You know, these ancient bodies we're studying and what the situation was, the language of the solar system, as it were. That's my pitch there anyway. Here we have a graphic illustration of the Rosetta spacecraft, which isn't actually that well designed for flying around a comet, but I might get to that later. It has solar panels, it's 32 meters tip to tip, which is 1.5 chains, which is how you measure a cricket pitch. It's about 3 tons launch mass. The Philae lander here is about as big as a reasonably sized washing machine and about 100 kilos. Over about, I'd say about 55% of the launch mass was fuel because we had to get so far away from the sun. Because we couldn't do a nuclear sample return and bring stuff back to a lab, you take the best labs that you have out to space. And that's what we have here. We have a nice suite of remote sensing and in situ. So things that are looking in different wavelengths and also smelling and tasting the comet as it's coming towards us. And also a wonderful plasma package to look at the interaction of the solar wind and the ionized particles around the comet. Same goes really for the lander. It specifically has a suite of instruments designed for if you want to actually go down and scratch and sniff a comet. And we have a nice package of instruments there. Churyumov-Gerasimenko is the comet we are going to. We weren't originally going there. There was a launch failure on an Ariane, so we had to rapidly change things within a couple of years. I think it was less than 2 years actually. And we chose this comet. It takes about just over 6 years to go around the sun, and Klim will tell you how to say it properly.
Churyumov-Gerasimenko.
So 67p. From our, this is basically, I think even now, this time last year is what we knew about this comet in terms of what its visual appearance was like. These are measurements taken from the light curve. You see fluctuations in the light curve from Hubble and other instruments, and you get an idea of the size of this thing and a shape. Grey potato, basically, that's what we thought of it. A grey potato with stuff flying off of it. So these are the things that we had an idea from observations. We saw that it wasn't just a diffuse coma, there were jets coming off or collimated regions of activity. It's a hot topic in the cometary community about whether you can say something's a jet or not. Well, I won't go into that. But point being, we had some ideas of what was going on, in particular the southern hemisphere becoming more active than the northern. Okay, so now here's a quick journey or the journey that we took to get to the comet. Even though we had 3 tons of spacecraft, 1,600 tons of fuel, we didn't have enough to actually get out. So we had to use the gravity of the Earth and Mars, the Earth 3 times, Mars once, to get out to the orbit of the comet. And we didn't just wait 10 years to get to the comet and not do anything. We had specific science targets to asteroids. We were also doing science during the flybys. This is an image on the left, on the top left, from the navigation camera, I believe, of Earth. And on that little funny plot is actually a plot of how the plasma from the solar wind interacts with the Earth's magnetic field. You have a bow shock in forming because this is supersonic. It has to get slowed down and diverted around the magnetic field of the Earth. We have the wonderful cluster mission that you may remember about. That's outside of this bow shock. It's upstream, seeing what's coming in the solar wind. At the same time that Rosetta was making, you see the little pink thing going down away from the sun. So it was inside the Earth's magnetic field, and the cluster was upstream, saw something coming, a current sheet, this layer of plasma that's separated by a shearing magnetic field, and that basically hit the Earth's magnetic field and made it ring. And we saw that with Rosetta and also ground-based magnetometers, which was quite nice. At a Mars flyby, we were able to combine measurements from the Mars Express mission with Rosetta. You get 2 points, you get a better idea of what's going on, constraining boundaries, and that gave us a better idea of how co-rotating interactions regions and CME, so structures within the solar wind, would interact with Mars. We could also take, just about see it, this is on one of the other Earth flybys. We looked up and Nick Howes and colleagues were able to image Rosetta, so that streak in the middle is actually Rosetta banging past. We combine the Vertis instrument on another one of the Earth flybys, which is an infrared measurement, with the ENVISAT measurements, looking at irradiance, and you use it for calibration, but also again, multi-point measurements, multi-spacecraft measurements are very nice. And then we took a selfie. There's no duck face here, and I've seen that Mars Curiosity is pointing at science targets, so that's Mars. There you go. No duck face. That becomes relevant in a while. Okay, we also did asteroid flyby. So we did asteroid Steins on the left, 2008, and then 2010 we did asteroid Lutetia. Kind of jerks towards you, this image. It's just because we ran the movie, the camera was taking shots at different cadences, so it looks a bit jerky. It wasn't staggering or anything. Conspiracy theory, right. These images you see here is a diamond-shaped asteroid, which is driven by an interaction with the solar radiation, and gravity actually causes this formation of a diamond shape. But certain people thought, actually, the reason we have this funny shape is actually it's a spaceship, and that's why we went with Rosetta to the Comet. That's nothing to do with the Comet. It's actually because we just wanted to fly past this alien spaceship that was shaped like a diamond. You can believe me, because technically I'm the man who is behind all of this. I wasn't at the time, but I'll assure you it was just a problem with the camera, which was rectified for the wonderful images we got from Lutetia. Basically, we were able to characterize their ages. There's a fantastic, I think it's about 20-odd kilometre sized crater, and you can see the kind of infall from that to give you an idea of how this is a very old object. But anyway, I won't go into that because I'm not that interested in rocks. And we got so far away from the sun that we didn't have enough power to power the spacecraft, so we went into hibernation. We had to put the spacecraft to sleep. And just before we did that, we pointed Rosetta up towards the Comet to kind of say, we're coming soon. Well, a couple of years, hopefully. Very noisy background. That's one of the problems we have with this from Earth. And so it went to sleep. In the meantime, stuff was going on. Ollie Haenel, and actually this is an activity strongly led by Colin Snodgrass, who's now at Open University, which is the ground-based campaign, which we needed operationally, but also scientifically, to check the Comet was there when we were asleep, that nothing was going wrong. And that's ongoing. If you go to this website, you can actually see which observatories are pointing towards the Comet. So we had Hubble, etc. You can have a look on there, and that's where the proposals go through as well. We also have an amateur community run by Padma down here. This is Padma, myself, and Claudia Alexander, the US project scientists, in the AGU conference last year. You can't see it down there, but there's a massive restroom sign which was causing some consternation when I tweeted that. It was the biggest toilet sign anyone had ever seen. Anyway, we also were simulating, or we have been simulating with the strangely named Working Group X, because they want to sound cool because they do simulations, looking at what they think the coma is to help us predict how we think the behaviour of the comet will be and how you fly our spacecraft around there, and also to constrain some of the measurements we have. A lot of the measurements we do are just in a point, so that doesn't give you much context globally, and you need simulations to add into that to kind of fine-tune the science that you're doing. I don't know why I did that. It's a new sign for science. Anyway, ground-based, as I was saying, so this is an ESA observation. No, this is from Nick Howes from the Rosetta Telescope. The comet's still there in 2012, very good. Then we were ramping up an outreach campaign, which I think is new for ESA. reasonably successful, I think, but I'll get onto that as we go along. We exited on the 20th of January 2014. Now, as I have alluded to you, I worked on the cluster mission. My mum didn't really know what plasma physics was, even though I told her quite frequently that was what my job was for over 10 years. But as soon as I told her I was moving to Rosetta, she said, I know, oh, Rosetta Comets, I know that. So now my mum knows what I do, basically. Actually, my kids think I'm cool as well, which is another bonus, but I digress. Then my mum said, oh, I know a song about Rosetta. Apparently, Georgie Fame and Alan Price made a song about Rosetta, and it was very poignant for the wake-up.
Rosetta, are you better? Are you well, well, well? Rosetta, are you better? Are you well, well, well?
Right, so that fitted reasonably well with the chorus, but if you listen to the rest of the song, it's about a girl who drinks too much and gets hungover all the time. So we were slightly worried with the whole analogy, but I thought that worked quite well. And of course, as we know, it was well. And this is what we were waiting for on the 20th of January, was a carrier signal, because the spacecraft was off. We didn't know anything about it. We didn't know whether there was a mission anymore. And that's why these people look so bloody happy, because they've invested decades of their life. In particular, Manfred Verhaal, who's actually retired, he was one of the original spacecraft operation managers. You have generations of them there, actually. He's like the granddad, that's the dad, and that's the son, and then you've got the other son, which is Sylvain Lodior. So you can see this progression of people who've been working on the mission. Manfred, Paolo Ferri, Andrea Camozzo, and then you'll see Sylvain later on, because he became the spacecraft operations manager in the interim period. Mark McCaughrean, the senior science advisor, and this is Emily Baldwin, who is the ESA _Rosetta tweet. So that's her typing hello world. And we had celebrations all over. We had the cartoons. This is one of my favorite PIs. This is Catherine Altveg from Bern. She has the gas spectrometer, Rosina, the thing that sniffs the comet. And we have Colin Pillinger and the Ptolemy team from the lander celebrating in the dark, unfortunately, there. So this is where we started to see people were a bit interested in what we were doing. We had a lot of nice media coverage. And we started to see Twitter reacting, and people were following us. And you do this thing where you can monitor hashtags, apparently. We saw that the hashtags to do with Rosetta and Wake Up Rosetta were percolating down to about 17 million people. So that was easy. So what were we doing after that? Well, we had to do a rendezvous maneuver to get to rendezvous with the comet. This is the important part here. We had to, when we came out of hibernation, we were banging along at 800 meters a second with respect to the comet. We're catching it up. Comet is doing about, was it 10 or so kilometers a second with respect to the sun. So we had to catch up with it, but also slow down at the same time and recoup this 9 million kilometers. And we did that in a couple of months. We were running this ad campaign, the whole, are we there yet? Child in the back seat, are we there yet, Mum? Are we there yet, Mum? You see the cartoons, I won't play them, they're too sad. And we started turning things on. This is a navigation camera. You can't see the comet here because it's pointing in the opposite direction. And then we had the science camera come on, the first light from the wide-angle camera of those series, and then the narrow-angle camera. And that dot there is the comet, which is nice. And then, again, ground-based to check where everything is and whether it's there. Can anyone see it? I'll help you quickly. There's the comet there. Okay, are we there yet? Nearly. We started to see the evolution of the comet. So that dot moving there is bang, all of a sudden the coma was appearing. And it's quite striking and slightly worrying for us. This plot we show here is actually this activity. So how much light, we're seeing a burst of light, and then it drops down again. This is actually still being discussed, what this is. Can we see that on the nucleus that we see now, what caused that? So it's another interesting point about this comet. And then eventually we got there, and here's Roberta Porter, one of the flight control team. Yes, we did. So what we see over here are the thruster temperatures, and this is actually the most well-behaved the thrusters has ever been. So that was quite nice to hear, but we were quite pleased that we actually managed to rendezvous with the comet for the first time. So we were there at 1 meter a second, walking pace with the comet, about 100 kilometers away from it. And we'd run this competition. We had a mountaineer won our competition of are we there yet? Andrea Camozzo is a mountaineer, so he found a nice analogy with some of the presentations that were made there, and also the Rosetta in a bottle was a nice feature as well. Like we started going over 200 million tweets at that point. People were getting a bit more interested. And then we went from potato to the duck. And then we started going, ooh, this is going to be tough. I like this one because it's to scale of what would happen. Scares everyone if it goes dark. Oh, the comet's going to come and hit us. As we're approaching, this is the approach in August. I'll take this opportunity to have a drink. Does anyone want some water? You're coughing. So this is a navigation camera. We're going towards, and then it starts to drift. Ooh, what's happened there is one of the manoeuvres we overperformed. And then the way that we phase the mission, so I think it's about 3 or 4 days later, all of a sudden the comet will pop back into view because it's where it's supposed to be again. There it was. And this is one of our first cool images, I guess, of full frame of the comet. Just for context, it's lost a little bit off the page there. This is one of these ground-based images run by Colin. In 1 pixel, right in the middle of that is the nucleus and Rosetta at this time. The size of that coma, the tail, etc., was already about 20,000 kilometers in August. And it's been growing ever since. I was talking about conspiracy theories earlier on, and you can go online, you can find a really cool YouTube video because it was apparently some guy got a letter from the ESA, or somebody working at the ESA, who wanted to tell him the truth, which was that we had photoshopped this image. And you see that little pit up there? There's a black thing just above, right there, up there. Apparently we photoshopped that in because actually there's a dome. And I think there's one on the head now. There's a structure that looks like a hangar, an aircraft hangar with some tracks around it and a couple of outbuildings that we photoshopped out. 380,000 people have liked that video. I was one of them. Well, it's from the Miro instrument. This is a sub-millimeter instrument. It actually can probe below the surface. Pretty cool. One of the first measurements we made was of how much water was coming off the surface as a point source when it was, bless you, so it was very, very far away. The equivalent of this measurement is like if you went out in your back garden and looked up at the moon and said, I can see 2 cups of water, like this, coming off the moon per second. So that's what they measured at the time to see what the growth in activity, the sublimation process. When we got closer, we were able to start seeing fluctuations. This is water production rate, fluctuating with a certain period of the comet's rotation. But there were 2 peaks and 2 troughs, as it were, indicating there's something a bit more complicated in terms of a uniform emission of gas. Then on this side here, if you can, this is basically looking at temperature with respect to solar irradiance, and it shows a good match between higher temperatures where most of the sun seems to be incident on the surface, and because this is subsurface, indicating that there is a low thermal inertia of the dust, so you're basically getting transfer of energy quite easily through this dust layer that we have found. Also, I'll point out, you see this plot seems to go to the left a bit. The blue goes past the comet. And I've forgotten to get my comet model out, but that is because the dark side of the comet we haven't observed properly yet, but we can see it in sub-millimeter. We can see it in a different wavelength of light, so we've probed it already. So that's why that goes off a bit more to the side, because they can. All right, this is from, remember Catherine, she was very happy from Bern. This is her instrument. It can smell the comet. And she can smell all this stuff. She can detect water, carbon monoxide, carbon dioxide, the volatiles, but also ammonia, methane, hydrogen sulfide, sulfur dioxide. So it's a bit stably, just a bit smelly really, so it's a bit like a stag do. Horrible stag do actually, but you're okay because you've got, there's a lot of alcohol in there. What we've also observed with Rosina is fluctuations in different volatiles, these gases coming off, depending on what's being irradiated. And what we see here, this is CO2 to water, where we're seeing more CO2 than water. And that's in one of the unilluminated patches. And this is a weird thing to now discuss as to why that's happening, why there are cooler spots and it has different sublimation coming off. And again, this is ongoing. This is kind of setting a line in the sand to say, right, this is what we think is happening now, and then we'll watch this progress over time. Another measurement is water. Again, going back to this flavors of water, deuterium to hydrogen. On the left, this is far away from the comet, these measurements. This is, Rosina is very, very sensitive. It can detect water. We knew it could detect water because it was detecting water coming off the spacecraft, part of the byproduct of the thrusters, etc. It can also smell the grease off of the actuator arm of the antenna, so it does smell quite a lot. But we knew it could detect water, which was good. So when we got to the comet, we were able to make these fantastic measurements of deuterium to hydrogen. I showed this plot before, where we had these Jupiter-class comets, which are basically comets that are within the orbit of Jupiter, like Churyumov-Gerasimenko, that had a deuterium to hydrogen ratio similar to that of Earth. But our comet was much, much higher. It's one of the highest that we've ever measured. What's going on? What that indicates, actually, is, well, it's likely that now asteroids were the dominant mechanism for delivery of water to Earth, but also that Churyumov-Gerasimenko is a very, very old object. It's a classic Kuiper belt object. It's been out there since the beginning, which means that our subsequent measurements will have that context, that that was stuff from right there at the beginning. Right. Dust. There's a lot of dust. And somebody in Italy counted it all. So this is a Giada paper. It's a dust detector, but they use the camera as well. What they're showing there are bound grains of dust, which are up to 2 meters in some circumstances, beyond about 130 kilometers away from the comet. And they believe that's what came off of the comet the last time it did its lap. So that's been stuck with the comet in the same orbit as it's come back round again. You've also got new emission. These are these streaks called BCC that you can just about see up there of the new dust coming off, but that's only in with about 20 kilometers. We can also see difference in the type of dust that we're seeing. So this is what this is showing. This is all the measurements made around the comet. So at higher latitudes, we're seeing more fluffy material. It's got less ice in it, but there's more dense packed material on the subsolar region, so the more equatorial regions. Again, giving you an idea, maybe there's something to do with activity that's driving this. We might be flinging off the first dust layer, which is again what was shown by these results. This is an image of single dust particles. It's a bit like some of you must have done it, when you stick your hand out the car in the summer, when you're a kid, going like that. And then there all flies stuck to it. So that's kind of what we do with this target. You stick it out in all the dust and then dust sticks to the surface. What's nice, because we're very slow, the dust doesn't splatter, it actually sits upright. So you see the 3D structure. There's a light on the side that shines and you see shadowing. And there's another light on the other side, so you get an idea of the 3D structure. But that's not all you can do with this instrument. You can look at its structure here. This is another paper which actually showed these dust particles were very crumbly. Gives you an idea again of their history. There's no ice in them. So these are fluffy particles. They crumble very easily. What you can also do with this instrument is shoot the particles. Now, weird thing, this team, because they have to discuss particles, they don't want to say, the one at 3,4 in terms of coordinates. So they name them. Aloy and Arvid. Boris was shot and found to be predominantly sodium with a little bit of magnesium. And this is key in terms of, again, seeing what the basic building blocks of the comet are made from. We've expected magnesium, but the sodium was quite a nice one. We've observed it from remotely, and now we're seeing it in the dust. Another measurement that's still being made, this is even smaller. This is an atom force microscope. It basically has a tip that moves up and then touches the top of the dust, then comes up again, moves along a bit and touches the top of the dust to scan it, get a 3D rendering of the dust particle. Problem is, the dust is a bit bigger than we expected, so this is what all this streaking is occurring. We're getting bits of it, and then the tip of the microscope is scratching the top, and we damaged the tip of the microscope here, but we're rerunning, things are looking good. Stay tuned. Plasma, okay. So what we're looking at here, you've got energy up the left-hand side and then time along the bottom. And the glowy stuff is things that's got more flux. So we're looking at ions coming from the solar wind. The reason it's blippy like that is because the measurement sweeps and looks to the sun and then comes back again and looks to the sun. So we're just concentrating on where we're seeing stuff. So we have ions coming from the sun, but also we're seeing water ions. These are being formed by the gas coming off of the comet being irradiated by the sun's radiation, that's what happens, and getting ionized, and then that gets pulled by the electric field that's in the solar wind in one direction. So we see it come in one direction, and then the solar wind is deflected in the other way, and we get the formation of a cavity, a bit similar to what we see around the Earth. Not exactly the same though. And also you can look at the magnetic field and how that interacts. And when you cause this kind of perturbation in the plasma, you generate waves. The waves are there to try and restabilize the plasma. You have an instability forming. And we actually see a wake structure that's got ripples in it. This is what I show on the right, but also you can sonify it, and this has been done. And you can make a song of the comet. So this is basically a sonification of this magnetic field data. About 5.8 million people have downloaded this. So, and I've always said that magnetic fields are really cool, and so there you go, I was right. What have we got here? This is some of the results from the OSIRIS camera, basically looking at the colour of the comet. It's very, very dark. I'll come to that again in a minute. But there are some slight spectral differences, so the neck seems to be a bit different to the rest of the comet. This middle plot here is supposed to show you where the illumination is dominating. What I'd just say about that is that the neck region has actually got 15% less illumination by the sun, because most of the activity we're seeing seems to come from the neck. So that's another head scratch. These plots on the bottom, this one actually shows you the angle of the dangle of the surface, basically, showing you that it's a very rough surface. On the left-hand side, that's really the gravitational potential of the body. Key thing, right, listen to this one. If you can jump 4 centimeters on now, well, don't stand up now. But anyway, if you can jump 4 centimeters off the ground here, if you could do that on the comet, you'd leave orbit. So it's very low gravity. Or you'd leave the surface and never come back again, which is one of the challenges for the lander, as we'll find out in a minute. So we can look at different wavelengths and see the spectral features and match them to organics and molecules that we know. And that's what we've done with Vertis. We showed that there's a very dark, we know that it's a very dark body. Although we see these images, they seem bright, it's a very, very, very black, dark, dusty object. Its albedo is something akin to less than Ashfeld. It's like printer toner. It's that kind of darkness. It reflects hardly any light at all. And that's indicative that there's a lot of organic-like material on the surface. And also that there's only about 1% of ice possible. We still haven't, well, we're getting inklings that there is some ice popping through, but that you've got this layer of dust. And from the measurements from Miro earlier on of gas outflow, that kind of matches what they're saying. The amount of gas they're seeing come off would only require about 1% of the surface having ice showing. It's a very variable surface, the comet. This duck shape that we have, and so we break it into different units depending on what the characteristics of the certain surface features. There are weird features that you can make terrestrial analogues, but remember this thing has got hardly any gravity at all, so certain things that you would envisage on Earth could not be possible on the comet. Just think if you're sat and you were coming down in towards the neck, which way would gravity actually be pulling you? These are the really weird things about this body, that if you were on the... Oh, hang on a minute, let me stop. Wait a sec. Talk among yourselves. Visual aid. Here we go. Here's a comet. So if you were coming down into the middle of the neck, the centre of gravity is there somewhere. So fine, you might get pulled to the neck, but then if you landed here, which way would gravity pull you down towards the neck? So there are these funny things about this comet that kind of perplex you when you start making these analogies. But one analogy you can see, you can't help it, are these like wind-driven features. You've got these wake structures around these blocks. You've got duning on the surface, indicative that there are low-lying winds. Weird. We also see these pits that may be due to porosity underneath and collapse of material. When you're getting stuff coming out and sublimating, that you might have caves forming and then things dropping down into these pits. But we're also seeing significant activity coming out of these pits or from around these pits. I didn't mention it before, but that mapping, it keeps with the Egyptian theme, and we've kept that as well by naming some of the smaller scale structures after Egyptian things. All of the regions are named after Egyptian deities, the ones on the head are female and the ones on the body are male, I believe. So anyway, we had Cheops, so called because it reminded people, or the collection of boulders we see up here reminds people of the Gizeh necropolis outside of, or in Egypt. And Cheops is the major pyramid. And for size, that's actually what it looked like. It's about 40 meters high, the boulder, or the block, or whatever you want to call it. And the actual pyramid's a bit bigger. This is a great one for conspiracy theorists. In some of these pits, we see these goosebumps, they're calling them, or dinosaur eggs. These are a scale of about 3 meters and seem to be persistent there. So this is really a surprise for people that we've got these 3 meter sized blobs there. Are they primordial building blocks? Is that what the comet's made from? Because that can help us understand how comets work in general. And again, this was very striking for us, but they don't occur everywhere. So it's not, it looks a bit like polystyrene or something when you break polystyrene up, but you don't see that at all boundaries. You don't see it in all pits. But it may be key in understanding the porosity of the body and how its density works and how its outgassing works. Again, I better hurry up here. On the neck region, we see different regions. At this boundary, actually, you can see as if in the direction of E there, as if the neck's being eaten away. And you remember that we're seeing significant activity in that region. And if we look hard and down into that interface region, we are starting to see spectral features that are very different to the surroundings. Possibly we're starting to see ice showing. So we go back again, think about this dust layer, you get rid of this dust layer. That's what we're seeing with the dust detectors as well. It's very fluffy material with not much ice. At some point, we think that layer is going to disappear and we'll start seeing more dense material with ice in it. And maybe that's what we're starting to see. We're starting to see we've gone down below the dusty area and we're starting to dig in and scratch into the harder surface, subsurface layer. Another nice feature, it doesn't show up too well here, on the left-hand side there is the neck region. And we see this very sheer cliff of about 900 meters. It's very nauseating when you look at this in 3D. And we actually have seen a crack forming. Now, whether this is to do with the, you've got this dual lobe nature. It looks like two things have smacked together, possibly. Is that why we've got a crack there? Or is it due to stresses between the two bodies? Or the head and the neck, as it were, that kind of thing. I didn't get a crack then, although I did get a crack in the neck anyway. Right, this time period, so from when we rendezvoused to the subsequent months is the most intense amount of operations that have ever been carried out on an ESA science mission. We had to map the comet. We've never been there before. We had to get closer and closer, spiral in to about 10 kilometers to learn how to fly around the spacecraft, but also to accurately map to get all the science that I've shown has been done during this time period. But the reason we were doing it was to do this, to select a landing site. And one of the striking things as soon as we knew it was this duck was, how the hell are we going to land on this thing? And in particular with this diverse morphology that we've seen, there's lumps and bumps and craters that are not craters. So it was a long summer for us. There's the team squashed in at the top into Toulouse, which is the science ground segment for the lander team, and colleagues here looking in 3D. Now, this is not a PR stunt to put your glasses on. It really helps get a feel for what the 3D structure of these things are. And I suffer from vertigo and I didn't like putting these on because, as I say, we've got this neck region that's got a 900 meter drop. It really helped for us being able to decipher from 2D. And eventually we came with this landing site at Jilkia, or Site J, which was the least worst of any of the landing sites. It's basically the best of the worst because it wasn't an easy thing to do, as we found out. There's the Comet again, using the new Curiosity science target nomenclature. So we had two selfies as we were going towards the Comet, and this time we've actually got a duck face in the selfie, because if we think of this as a duck, that head is face forward. I did think it was the other way round, so it was a duck something else, but it is the face. And then, once we had chosen, we had to go in some we decided how we were going to configure ourselves to deploy the lander. And so we approached 12th of November and deployed at 23 kilometers. This is the glass house, the room next to the main control room in ESOC. You can see, well, you can't see very well. This is Andrea Racamazzo. This is Fred Janssen, the mission manager. The man is in charge of everything. He was the one that said, yes or no, we're not going to do this, we're going to do that. Not many people know that, but he was the one that was in control. Although the flight control team were there and the flight director, Fred is the mission manager and is in charge of the entire mission, but not in charge of me. Anyway, and then Stefan and Jens and Ilse there, and that's Sylvan. What was I talking about? Yeah, okay, so this is about 9 o'clock in the evening, and there have been some problems with the lander. So this is a crisis meeting. That's why Andrea's going in Italian. And he was heard, actually, apparently. There were some issues with the lander. We had to go through a procedure to say, right, what are the criteria to allow us to go to a go scenario, to actually do this landing? We set the criteria, you write it on this whiteboard, which is a cool whiteboard that you can press a button and it gets scanned and made into a PDF. So they all had to sign this whiteboard and then it was scanned, and that was basically the criteria. About 11:30, that was all done. Things were sent up to the spacecraft. Fred and I went back to our hotel rooms, but then we said, right, we'll have a quick drink first. We went to the hotel and the bar was filled with people like Chris and all journalists really wanted to talk to us, and we really didn't want to talk to people. So we went into the smoking lounge because that's the only place where nobody was, and then had a little crisis discussion with the communications people, who then went back to ESOC as well to go, right, what's going to happen if we have to not do this? At about 3 o'clock in the morning, I got a text from Fred, who'd got a text from Larry O'Rourke down in the Lander Control Centre, and ESOC, basically saying, we go. And so I got up and went to ESOC. And so a couple of hours later, we were able to have this image. So this was from Philae pointing back at Rosetta. It's a bit blurred because the orbiter was rotating. And we have this lovely set of images now. And I like this analogy as a cat. You see, it was good for us to see because the legs had gone out, but that meant that we were going to hopefully land okay. And if you think of the analogy with a cat, and when I was a kid and I was terrible trying to see if you can make a cat land on its back, you can't. I tried it quite a lot, but that was, that's why I like this analogy, because it was the right way. It was always going to be that way. Then as we got closer to about 40 meters off the surface, so that boulder there is about 5 meters across. This is the ROLIS camera. Well, I better bang on now. And then we were very happy because we landed. And to prove that, that's me there behind the glass. There's Manfred. Because we were really constrained as to who could go in the MCR, but Manfred and I were sort of stuck like a couple of Garfields on the window. And it was really useful being with Manfred, who'd had like 30 or so years of operations experience, basically saying that parameter should be 5, that parameter should be 7. It's going to happen in 7 seconds. And you're like, But then it did a couple of seconds later. And of course, we found out, actually, there was a different picture for the control room in Cologne, where the lander people, they were not doing this. They were going to do their champagne, and they went, something's wrong. And subsequently, something was wrong. This is the image, this is actually the first image from the surface of the Comet. So you can see that something went wrong. The software's not worked properly, and also it's all blurry because the Comet was moving. And this is indicated here, and these 2 frames from the nav cam, you can see before, after. Right, so you see the impact, and I can't see it very well. There's basically a lander and a shadow as it's rebound. It's better shown in this set of images where we see the trajectory coming down, hits the surface, and then goes for a little jaunt over here. The before and after, you see these 3 dents in the surface. We're still looking at that because the dents don't match up the size of the feet, so something else must have gone on. And that's an ongoing analysis. It wasn't just a flat landing. Oh Christ, that scared me. Yeah, that's the sound of the lander. There are all acoustic sensors on the feet, so that's actually really what nobody can hear you scream in space, can they? But that's the measurements made by the feet. Gives you an idea of what the tensile, the elastic stresses and everything on the dust layer on the surface. We now know that we went on a little jaunt about 1 kilometre up, about over 150 metres high in some parts. We clipped something, we could find that out by, this is magnetic field measurements. Every time you whack a piece of instrumentation like this, you'll generate magnetic fields because it's not supposed to be whacked. So by whacking on the surface, we were getting nice magnetic field spikes. We could also get it from other housekeeping data. We could also use the magnetic field to show that on one of these, it had clipped something and started to tumble. So you see changes in all the components of the magnetic field. I'm going to start speeding up now. Then we have these images from Shiva when it ended up in the ditch. See, there's still a stag do analogy here somewhere. Using the images here, we've started to reconstruct, or the colleagues from SONC in Toulouse started to reconstruct where they think the lander is laying. We've got this image. We've really got into some pristine material. We could never have dreamed to be in this situation because we've really got into something that's super old. Biebering, the PI of Shiva, has a plot like, it shows this image, but he's got an arrow to the foot saying 20 years old, and then an arrow here saying 4.6 billion years old. I like this one as well, a bit like the selfies, but here you've got the imposition of something we made on some completely alien object. Those glows are the reflection of the sun up onto the cliff that's overhanging the lander. We've got an instrument on called Concert on the orbiter and the lander, which fires radio waves. That basically gives you a tomography, but also can allow you to do some GPS location, and we have a rough idea of where the lander is. Again, but from trajectory. I mean, ultimately, the key thing here is there was the target, and the touchdown was only within about 120 meters from 23 kilometers away, which is why Stefan Ulemek, the project manager of the lander, is shaking the hand of this man, who is Vicente Companies, who is the lead flight dynamics guy. He's one of the special people that can come up with all these orbits to allow you to fly around the comet. So it was successful. I'm a glasses half full person. We got measurements from three parts of the comet, which we never would have dreamt. This music, does anyone know what Blade Runner is? The film Blade Runner with Harrison Ford. Vangelis did the music for that. He was also kind enough to do some music for the landing, so that's what that is. I'll shut him up for a minute. But we had a lot of good coverage. Here we nearly reached about 1 billion people in the tweets, so that was quite good. Maybe it's because of other stuff. So we got a Google Doodle. We got the New Year's one. We'll get a comet come in a minute. Look, there you go. It's like, boy. We had the astronauts mucking around, pretending to land on comets. So Alexander Gerst with an earplug and a bit of Velcro. That is not the first time he did that. And also, we had a feature film. Oh, it was a 7-minute short. We had to do something like Curiosity, but we did something different. I quite liked it. Important stats. On the bottom, this is people being asked in Germany, France, Italy, and the UK, what's Rosetta? And that's the correct answer, the people that had answered correctly. Okay, the UK is the one at the bottom, but nonetheless, 70% of people and more knowing what's going on is pretty good. So what's going on now? This is my crew down in ESA. These are the liaison scientists who kind of push via the PIs the science into the top of the system. We're planning where we're going to fly by, co-rotational flybys. We're looking at what the activity of this comet's going to be and predicting it. These are plots of where we think, right, if we do an orbit maneuver here, we have this much time and there'll be a deflection because of the outgassing of the comet. We then have to do a check of navigation here, and then we see how far we're out. There's all this stuff going on, and we do it twice as well because we have a preferred case of what we think the cometary activity will be, how close we can get to the comet. Then we have a robust case just in case everything goes wrong, and we plan those in parallel all the time. It's a quite intense time, and that's why they all look a bit crazy. Okay, so recently we did this flyby. So we came out of bound orbits. The outgassing was too much given the constraints that we understand with the spacecraft, so we had to start doing these flybys, these weird orbits. So 14th we came very close. This is the approach phase. We start to see the comet, or going towards the comet. That little judder is actually the navcam doing a raster. That's why we get these 4 plates here, because you do a raster to capture the entire comet. So this is the approach phase, and then this is the navigation camera from closest approach. So we were getting in within about 6 kilometers. I can't show it to you today, but on Monday you will see the narrow angle camera from OSIRIS image, which shows you a full frame that's about 220 meters across. So the pixel resolution is about 11 centimeters, so it's pretty good. This is the Imhotep region, the Cheops boulders up there. You can see some of the cool features. They're not on the side, yeah, but there's some stuff that looks like stuff you see in snow called sun cups and dirt cones and whatnot. No yellow snow though. But, okay, and then subsequently we're going to go and do all these other weird orbits, far flybys, near flybys, and we're going to fly around this for a number of months. It's starting to become active. We'll go through perihelion in August, and technically we end at the end of this year, but we're looking to hopefully extend the mission. Ultimately, we're limited by the fact we start to move away from the sun. So we will have to go, well, we'll be in the situation as we went into hibernation, there's not enough power. Also, we'll be bingo fuel by then. There'll be nothing for us to maneuver with. The current discussion is that we will deorbit onto the comet. Slowly getting closer and closer to do really cool measurements and then land for a 4th time. So Rosetta is the first mission to shadow a comet, travelling at relative walking pace. Very important, we're doing it for over a year. It's the first time we've landed on a comet, more than once. And it already has given us more information about comets than we've ever had before, and we'll continue to do so. And that's about all I'm going to say now. Stay tuned with that, and I forgot to put my email on, but you can come and ask me later. Perihelion, no will end a mission, but I think we're going to go further. Thank you very much for your attention. Thank you.
Okay, we're going to take questions from Matt really quickly. 3 questions.
Sorry.
So you said you thought the comet was a really old one, and we saw the surface, and you've like characterized it by those Greek by those names.
Yeah.
So why is the surface not more uniform, given how old it is, and given why is there differentiation of the surface?
Well, that's what some of the questions we want to ask. The comet, in hindsight, appears to be a very good choice of a comet to have gone to, but we didn't know that because we thought it was a potato a year ago. There's you know, they've allocated these descriptions. If you go to this, the Nick Thomas paper where they do this naming of via Egyptian deities, here's a flat surface. Here is a consolidated surface. Here is a dusty surface. So it's basically they've gone at the lowest common denominator visually what they think these different regions are. Then that gives them context for comparing them in different wavelengths for other instruments. That's what we're doing now. We're trying to work out why the hell you've got regions that look near enough pristine. You've got these dinosaur cluster eggs or goosebumps, and then in other places you haven't got them and you've got dust. What are those blocks? How have they happened? Is that downfall from these cliff structures that have collapsed and then you see this stuff rolling down? It's something we're looking at now. It's just weird, basically. Oh, he's well lazy. He just went, oh, I'll give it to you.
Okay, so Philae landed in something of a ditch, and I heard at the time that there was hope it would turn back on when you come towards perihelion.
Yeah, at the moment, right, I kind of skimmed over that quite quickly. The point being there were 3 phases of Philae's life. It was going to be a first separation descent and landing. It did that well, we did landing a bit more. First science sequence, about 60 hours. We had to modify certain things. Then it was going to go into hibernation anyway and then go into long-term science. That's where it is at the moment. But it's covered by this cliff area. We think the illumination will improve. We know the illumination will improve. What I was saying earlier on about that we know the southern hemisphere will become more active. That's the bit on this side where it's dark at the moment. And that will mean that the back head here will become more illuminated in May time period, which is where we think the lander is. So the sun will be in a better position with respect to the surface of the comet to illuminate the lander. Also, we'll be closer to the sun, so we'll get more input. We are going to listen for it in March. So we start listening for it. We turn one of the ears on the spacecraft. We don't think it will be full powered then. It might say something. Then the next month we'll do it again. It might be a bit better. It has to get to a certain level to be able to reboot, but it's doing what it's designed. It's asleep until it gets enough power. We hope by May it will have enough power to come back on fully. Glass is half full.
When you were saying before about how low the gravity is on the comet and how little it takes to go off in an escape trajectory, if you'd landed sort of on the equator with relation to the spin, as it were, could it have been a problem that it could have kicked you off into a
No,
escape
I
trajectory?
think, yeah, so basically the centripetal or whatever it is, I always forget, acceleration is about a third of the gravity. So, I mean, that's another thing of this, the fact that it's got such low gravity, the fact that you've got it spinning, that's kind of destabilizing the body anyway. But we are actually aiming for around the equator because it makes it easier from a flight dynamics point of view. It was only, so the spin is like that. So it's kind of, that's the spin equator there in that plane, and we are aiming over here somewhere. So it's kind of close to the equator because it's the better region for illumination. To cycle, one of the better places to put the lander is somewhere where you're getting good day and night, because you need to power it, heat it, and then let it cool down. So that was why the equator was a good region. Well, ultimately, it didn't want to do that. Quick anecdote, the original lander, so when we went from the sample return, the mission was supposed to have 2 landers. And one of the landers was a Comet hopper, and this was a proposal by a great scientist, Helmut Rosenbauer, who's unfortunately quite ill at the moment, but it's as if the lander didn't want to do what it'd been told, like a naughty child, and wanted to do what Helmut had thought about, which is to hop across the comet. And that's, as I say, it's cool that we've got these measurements of the magnetic field, we've got dust measurements, gas measurements from Ptolemy at least, from different spots on the comet.